We are counting down the 12 most baffling mysteries that turn everything we thought we knew about interstellar visitors upside down. From oddities in discovery and unexpected biases behind the initial observations, all the way to chemical contradictions no comet model can explain, each entry challenges mainstream science in ways you will not believe. Which anomaly stands as the biggest threat to the official narrative? Let us begin with number 12. Discovery of 3I Atlas began with a faint streak on Atlas survey images in July 2025, captured at low solar elongation, barely above the horizon and deep in twilight. The initial alert triggered a global scramble among observatories, but most data stayed locked behind embargoes for weeks. Early measurements depended on the cadence and filter choices of the Atlas pipeline, which prioritized rapid detection of moving objects over detailed characterization. This meant key details like precise brightness, color, and even motion were filtered through automated processes built for asteroids, not interstellar visitors. With major telescopes racing to secure observing slots, teams were forced to interpret limited, sometimes incomplete data, while embargo culture kept raw frames and calibration files out of public reach. The first month of analysis was shaped as much by these procedural bottlenecks as by the object's own physics, setting the stage for debates that would unfold as more data finally emerged. Initial images from the Atlas survey offered little more than a bright dot, no sign of the spreading haze that marks a classic comet. As astronomers pulled up the earliest frames from July 2025, the object's light profile stayed stubbornly compact, matching a point source rather than the fuzzy glow of dust and gas. Even as its brightness crept upward, follow-up teams reported the absence of an extended coma, raising eyebrows in survey logs and fueling early skepticism. In typical comets, solar heating triggers volatile ices to sublimate, releasing gas and dust that scatter sunlight and form a visible envelope. Here, the coma remained faint or unresolved, suggesting an unusually low dust-to-gas ratio or a fundamentally different activity process. This first visual anomaly set a baseline. Whatever 3I Atlas was, its early behavior didn't fit the standard comet playbook, leaving observers to puzzle over the physics driving its muted display. Polarimetric analysis serves as a forensic tool for separating dusty comets from bare, rocky bodies, yet for 3I Atlas, the most telling data are missing. High signal-to-noise polarimetry at phase angles above 40 degrees, essential for diagnosing particle size and surface texture, remains unpublished. Without these measurements, the debate over whether sunlight is scattering off a cloud of fine dust or a solid exposed nucleus stays unresolved. Meanwhile, amateur and professional color photometry has hinted at something odd. Preliminary albedo estimates drift outside the familiar 2 to 10% range seen in solar system comets. The object's color indices, gathered by pro-am networks, do not settle comfortably into the expected cometary palette either. These gaps and outliers in the light-scattering data keep the surface composition in question, adding another layer of uncertainty to the optical profile of 3I Atlas and fueling speculation about what, if anything, cloaks its core. Radio telescopes like Meerkat tuned in as 3I Atlas crossed the inner solar system, picking up crisp molecular lines, signals from hydrogen cyanide and methanol drifting in the vacuum. These detections pointed to active chemistry, the kind expected from a comet venting gas. Yet when infrared observatories, including NEOWISE, scanned the same region for heat, the results were almost silent. At wavelengths between 10 and 20 microns, where a warm, dusty nucleus should shine, the flux barely nudged above background. The upper limits set by these thermal searches suggest either an object smaller than a kilometer or one with an unusually dark, non-reflective surface. This direct clash, radio evidence of volatile molecules without the matching thermal glow, drives a wedge between what is seen in different parts of the spectrum. For astronomers, it is a puzzle. The chemistry is there, but the expected warmth is missing, deepening uncertainty about the true nature of 3I Atlas. High-cadence photometry from ZTF and Pan-STARRS captured a restless light curve, with 3I Atlas swinging in brightness by up to half a magnitude on timescales of less than an hour. These wild fluctuations defy the smooth, predictable brightening that comes from steady ice sublimation on a rotating nucleus. Instead, the object's brightness darted up and down in irregular bursts, sometimes fading and recovering within a single observing run. The amplitude of these changes outpaces what is usually seen from simple rotation or even patchy outgassing on solar system comets. Such erratic behavior hints at a surface prone to sudden, possibly explosive venting, or perhaps unstable regions rotating in and out of sunlight. The time domain record adds a layer of temporal instability to the puzzle. 3I Atlas refuses to settle into a steady rhythm, raising questions about its internal structure and the forces driving its activity. High-resolution images from Hubble and ground-based telescopes captured a nucleus bristling with activity, 7 distinct, tightly collimated jets streaming out from separate points on 3I Atlas. Each jet carved its own path through the surrounding material, forming a tangled web of outflows that defied the classic single-fan structure seen in most comets. Some jets flickered on and off across just a few hours, while others appeared to twist and split, hinting at the presence of deep fissures or vents opening and closing as the object spun. In several frames, faint streaks and doubling at the nucleus hinted that parts of the surface might be breaking away, though no confirmed fragments have been tracked. This mosaic of localized eruptions suggests a patchwork crust, some regions violently active, others eerily quiet. The complexity of these jets and the possibility of fragmentation points to a nucleus under stress, shaped by forces that remain only partly understood. Orbital calculations from both the Minor Planet Center and JPL leave no doubt 3I Atlas is not bound to the Sun. Its path is hyperbolic, with an eccentricity greater than 1 and a velocity that exceeds the solar system's escape speed by a comfortable margin. The IAU's official designation, 3I, places it alongside only 2 other confirmed interstellar visitors. What sets 3I Atlas apart is not just its trajectory, but its speed. It entered the solar system faster than either 1I Oumuamua or 2I Borisov, racing through the inner planets with barely any time to absorb solar heat. This rapid passage means less time for sunlight to warm the nucleus, limiting how much ice can sublimate and how much gas or dust can escape. Standard comet models expect a slow build-up of activity as an object approaches the Sun. For 3I Atlas, the clock runs faster and the rules of outgassing change. This dynamical context frames every debate about its chemistry and behavior, setting the baseline for the next puzzle, how its motion defies even gravitational prediction. Residual plots from JPL and the Minor Planet Center show that 3I Atlas doesn't follow the path gravity alone predicts. Over weeks, its position drifts by tens of thousands of kilometers, small on a cosmic scale, but far beyond the margin for error in modern astrometry. This non-gravitational acceleration, called NGA, is measured as a persistent sunward push, with a weaker component along its orbital track. Analysts Tholen and Farnokia have fit both radial and transverse acceleration terms, finding a signal that stands above millisecond level noise. Standard comet models blame such deviations on jets of gas venting from the nucleus, but here, the magnitude and timing strain those explanations. Carbon monoxide and carbon dioxide outgassing could, in theory, provide a gentle thrust, yet the observed acceleration is weaker and more sporadic than those models predict. The numbers don't quite add up, leaving a physical force discrepancy at the heart of the 3I Atlas puzzle. Competing explanations for 3I Atlas have multiplied as each anomaly stacks up. Some researchers propose it is an unusually exotic interstellar fragment, perhaps a piece of a shattered planetesimal carrying chemical fingerprints from a star system unlike our own. Others argue for a mostly inert asteroid, coated with a thin layer of ices or dust, its fleeting outbursts triggered by surface processes rather than deep, volatile, rich interiors. The most speculative voices suggest artificial origin, a manufactured probe or relic, its odd chemistry and motion the result of engineering rather than nature. Avi Loeb has publicly called for open-mindedness, pointing to the sharp nickel-to-iron ratio and non-gravitational acceleration as possible markers of something non-natural. Mainstream astronomers, however, point out that cometary diversity is vast and that interstellar objects are expected to defy local norms. Each alternative faces its own hurdles. There is no clear evidence of artificial structure, no consistent signs of inertness, and no precedent for such extreme chemistry in known fragments. The debate now hinges on which hypothesis best survives the coming chemical tests. Spectroscopic analysis of 3I Atlas delivers the most direct challenge to the comet hypothesis. Keck and VLT spectra reveal a water content of just 4% by mass, an order of magnitude below the 30 to 80% seen in typical solar system comets. Instead, carbon dioxide dominates, with a carbon dioxide to water ratio of 8:1, far exceeding even the most volatile rich comets ever catalogued. The surprises don't end there. The nickel to iron ratio clocks in at 12.5, while most comets barely reach a value of 3. The nickel to cyanide ratio is also elevated, pushing beyond the upper limits found in any prior survey. These numbers do not fit the chemical fingerprints of known comets, whether local or interstellar. Mainstream astronomers argue that interstellar origins could explain the extremes, but the sheer scale of the anomalies, especially the depleted water and metal ratios, has left even seasoned cometary chemists searching for precedent. For some, these values hint at a formation environment or process far outside anything yet observed, raising the possibility that 3I Atlas is not a comet in any familiar sense. Across all 12 anomalies, one pattern stands out. Our best models cannot fully explain what 3I Atlas is or is not. In cosmic mysteries like this, science advances not by the answers, but by the questions we are forced to ask next. The universe still holds its secrets tightly.